All right, and I think we are getting set up. We have like,
Perfect.
it takes a sec to connect. But it also records it, so people like can see me just staring at the screen.
Perfect. Yeah, I'm going to share my opening slide and then I'll
Okay,
unshare,
yeah.
and then unshare when you're doing the intro. So.
Okay, sure.
Perfect.
Yep, we can see that. But it also records it, so people like there we are. That's me on Facebook.
Okay.
All right, perfect. So I'm all set up. Welcome back, everyone, to Ask a Scientist with the Asheville Museum of Science. My name is Abby, and I am an educator with the Asheville Museum of Science. Today, we have with us Dr. Tim Siegler. Is that how you say your last name?
Yep, correct.
Okay, great. Dr. Tim is a postdoctoral researcher in the lab of Dr. Hugh Hillhouse in the Department of Chemical Engineering at the University of Washington. He has tons of experiments working with solution process photovoltaics. We are going to learn what that is. So that's exciting because I'm not even really sure. So I'm just going to pass it over to Dr. Tim and he can explain everything to us. Don't forget to send in your questions. I will pass it off to you, Dr. Tim.
All right. Thank you very much, Abby, and thanks for having me here. It's always great to share the science that we're doing in lab with the greater community and people, and really just expand like what perovskites are and be kind of a disciple for perovskite technologies. So today I want to talk about solar cells in particular. And in an earlier session of the Ask a Scientist series, there was already a talk about solar panel technology, which dealt with how you actually take a solar panel from, say, Home Depot and deploy it and install it and track its electricity generation potential over time. But I am a material scientist more than that. And I'd like to crack open the solar cell today and tell everybody what's inside and show people what's inside and what could be inside in the next generation of solar cell technologies. And so before I begin, a little introduction of myself. So I'm Dr. Tim Siegler. I am a chemical engineer by training, got my bachelor's at Notre Dame, got my Ph.D. at the University of Texas at Austin, and have work and research and training, teaching experience in various different parts around the world. While I am a chemical engineer by training, there's not a lot of fundamental chemical engineering research going on. So if you're doing heavy research in chemical engineering, it's usually highly interdisciplinary with other types of science, either protein engineering or polymer engineering, or in my case, materials science. And material science is at its core a highly interdisciplinary field related to the discovery and design of new materials for useful applications. Basically, material scientists like to think of themselves as the fundamental underpinning of all of their types of science, because without the materials, you can't do the experiments that they do in physics, or you can't have the chemistry that, you don't have the chemistry background that you need to do some of this chemical research and things like this. And some of my areas of expertise, aka my favorite materials, include semiconductor materials, materials that interact with light. So solar cells fit into those first two categories. And I also have expertise in phase change materials. So if you want to talk about materials that change color and phase, I can answer some questions about that too. And so before we begin, I think it's good to hammer down what some of the basics of what I'm talking about when I say solar cells, solar panels, and photovoltaics. And at the beginning, I kind of had a little bit of a prompt that I wanted people to start thinking about in terms of solar energy and solar panels and solar cells and things like this. And talking about what their sort of experience was with solar from the general culture. But at a fundamental level, solar technology is trying to answer the same problem that every type of electricity generation technology in the world is trying to answer, which is namely that everything in the world that we're using, that we use basically in the modern economy, is based on electricity. You're watching this very stream because you're looking at a laptop powered by electricity. You have electric lights in your homes, electric appliances, use it to cook, and everything else. And so the problem, though, is that nature does not provide us, outside of a random lightning strike here and there, with natural sources of electricity that we can utilize to power our homes and devices. And so all electricity generation is based on conversion of different types of energy to electricity. In the case of wood or oil or gas or coal, you're converting biochemical energy to thermal energy, and then that thermal energy is converted through a turbine process to electricity. For, let's say, a hydroelectric dam, you're converting the gravitational potential energy stored in elevated water to mechanical energy as that water falls to lower elevations. And then solar more directly converts the energy stored in the light of the sun that hits Earth to electrical energy, again, in a very direct process. And as we're talking about solar cells and solar panels, I want to talk about what some of this vocabulary that I'm going to be throwing around is. Solar panels are the terms you may be familiar with most because those are the commercial products that are marketed and sold to members of the general public. And essentially a solar panel, which I don't really use a lot in my research, is a grouped system that converts sunlight to electricity. Basically, you can think of a solar panel as a sort of black box, as we call it, that takes light in and gives you electricity out. A solar cell, on the other hand, are the smallest components of the solar panel. I think an imperfect definition of a solar cell would be the smallest subunit of a panel that still can convert light to electricity with the same efficiency as the larger panel. And then I talked about photovoltaics earlier, and we were talking about what, you know, that's a bit of a scary word for some people, but in essence, photovoltaics is just a fancy way of saying anything that converts light to electricity, whether it's on the panel level, on the solar cells level, or if you have some creative idea of your own where you're taking light energy and converting it directly to electricity, that is also a photovoltaic. And for etymologists, photo from the sun, voltaic, electricity. So that's basically, whenever you hear photovoltaic, just think, oh, he just doesn't want to be specific right now. So now, as a material scientist, I really like the materials part of solar. And so there's three major types of materials that are used in most of the solar panels in the world. And in fact, probably you could say there's only one real material used for most solar panels that you'll see. Silicon technology has been dominant since the 60s as far as solar technology is concerned. And even in 2017, 95 to 97% of all panels that were installed in the world were silicon-based solar cells. It's silicon, not silicone, by the way, but yes, that is another important aspect of that. So it's a silicon-based solar panels in most of the world. If you see a silicon, or if you see a solar cell or solar panel anywhere, you can safely guess that silicon is probably the material used to convert light to electricity. But there are types of other commercial solar panels that you can buy if you're looking for them. Cadmium telluride is a technology that is directly competitive with silicon, and actually something that I think is a much more promising technology than silicon. And in part because cadmium telluride technology works better in warmer climates. Up here in Washington, a silicon panel is going to be much more efficient than a cadmium telluride panel. But down in North Carolina, or potentially further south than that even, or in northern South America where it gets very warm, or in northern Africa, other places like this, cadmium telluride can be more efficient than silicon and has taken quite a foothold. However, it only contributes to about 3% of all panels worldwide because there's only a single company in the entire world, First Solar out of Colorado, that knows how to make cadmium telluride solar cells efficiently. And so because of this inherent supply limitation, you don't see much cadmium telluride in the world. And then a more recent development is copper indium gallium selenide, or CIGS. This material is a bit new, and it's very popular in Japan relative to the rest of the world. And it's going to be interesting to see how much market share copper indium gallium selenide will have compared to these other two, given there's not too much competitive advantage in any single respect. So there's a question.
Yeah, so Cassie is asking, why does it make a difference by location?
Yeah, it has to do with climate, average temperature. So with silicon, your efficiency is, for any technology, I'll say, start from there. With any technology, your efficiency is not constant as a function of temperature. So as you go hotter and colder, your efficiency will change. With silicon, the colder you are, the more efficient your solar cell is. And with cadmium telluride, the hotter you are, the more efficient your solar cell is. And so because they have this opposite trend, this is why cadmium telluride might be more competitive in certain warm environments. So, all right, great. That's a great question. Thank you for asking. Cool. And so before we get into the talk about the present and future, I want to just go through one demonstration using silicon, the dominant material technology right now, to describe how solar cells work. And it's important to note that even in a silicon-based panel, you don't have one type of silicon in the entire panel. So yeah, silicon is we're talking about elemental silicon, by the way. And so you actually have two different layers that are stacked on top of each other directly. In one of the layers, you replace the silicon with a little bit of phosphorus, and it doesn't have to be much phosphorus. In fact, I think average doping levels are around 1 in a billion atoms of silicon is replaced with phosphorus. But this makes a big difference for the electrical potential of this layer. Silicon, if you look at it on a periodic table, it has 4 valence electrons, which means 4 electrons available to fly around this crystal as far and wide as they want. But phosphorus, on the other hand, has 5 electrons that are available to the material. And this extra negative charge, even in very, very small concentrations, has a dramatic impact on how negative this layer is. And so we call this layer N-type because these extra electrons are here, making that layer a little bit more negative. This is an oversimplification. For technical experts who may be watching, I'm talking about raising the Fermi energy of this layer through N-type doping. Similarly, in the other half of the layer, you replace silicon with its 4 electrons with boron, which only has 3 electrons. Because the material, and you do it at the same concentrations, about 1 in every billion atoms. And because boron has a little bit more, has this missing electron, that's a missing negative charge, that's going to make this layer similarly much more positive. Now, interestingly, as you put this positive layer and this negative layer together, what happens? Well, the positive charges from this layer come and combine with the negative charges from this layer and create a potential across this where charges can move, are forced to move from one side to the other. Then when light comes in and excites electrons at that interface where the p-type and the n-type layer come together, because of some physics and some interest, and because the n-type layer is a little bit more positive at this interface than the rest of the n-type bulk, and the p-type layer is a little bit more negative than the p-type bulk, counterintuitively, these excited negatively charged electrons go into the n-type phosphorus doped silicon layer. And because they're going sort of to a more negative side, you can extract these electrons and generate power this way. And so at a very, very simple level, this is just the basics of how solar cells generate electricity from light. Great, so now we have this understanding of what solar is, what the vocabulary is, and how they work. Why is solar interesting, though, for us, for society, and for scientists? And I want to take this from a historical perspective, because I think it's interesting to note that solar energy became something that is not just a chemistry experiment, but an actual product at Bell Labs. Bell was an old technology monopoly, or an old telecommunications monopoly from the 40s, 50s, and 60s that had this very robust research program called Bell Labs. And in the 50s, they were trying to enter new technology sectors using their superior knowledge of semiconductors. And so they wanted to see okay, well, there's a lot of money being made on coal and oil. This is in 1954. They wanted to try to create electricity using semiconductors to compete with this coal and oil and try to take some of the electricity market. And so in their labs, they were able to invent this um, solar panel, the silicon-based solar cell. And actually, a similar motivation is how we got the lithium-ion battery. Bell Labs also invented the lithium-ion battery as well. So a lot of the modern green economy, green electricity generation economy can be traced back to Bell Labs. And initially, they wanted to use this to sell batteries and generators. They wanted to actually sell wholesale electricity, but it was so expensive to make this solar panel, and so few electrons came out of it, they could only sell batteries and generators. And outside of a few new age toys, this never really took off, despite these swanky looking advertisements from the 50s. And so it looked like solar was going to die after about 5 to 10 years of Bell Labs trying to make it take off, until some folks at NASA, that organization you might be familiar with, heard about solar technology and solar electricity generation sources. And it turns out that solar was perfect for these new satellites they were hoping to launch as part of the space race. You think about what satellites do. If you're going to launch something into space, into near Earth orbit, you want it to be able to take scientific measurements, to take pictures, and to communicate back to Earth everything that it finds. And all those three things, data collection, photo taking, and even the transmission of data back to Earth, require electricity. But because it's so expensive to launch a pound of material into space, to increase your satellite weight by even 1 pound, you don't want to have to rely on things like coal or oil or gas, or even next generation fuels like liquid hydrogen to power as an electricity generation source, not just because it's heavy, but also because these fuels run out, which means that as soon as your fuels run out, your satellite is now just a piece of metal floating in space. But with these solar cells, while they weren't very efficient and they were very expensive, that didn't matter as much to the satellite people, because you could launch one of these probes into space and you could power it for as long as the solar cell lived, which at that point was 10 to 20 years. And so you could have much longer missions, and get a lot more useful data and a lot more surveillance from these initial satellites that were launched into space. And so in a way, NASA and the space race saved the solar cell and kept it from going into complete obscurity. And that's Dr. Hans Siegler, who saw the potential for this sort of application. Then in the 70s and 80s, folks started to really get attuned to this idea of anthropomorphic climate change, this idea that we were polluting our environment, our gaseous environment, with a lot of carbon dioxide from fuel oil, from coal and natural gas byproducts. And that this, well, in the 70s and 80s, it was hard to see the temperatures going up globally, but the potential was there. People started recognizing that this could be a significant issue, as the greenhouse effect could cause a significant rise in global surface temperature, which we're seeing a lot now, especially here in Seattle, which is covered in a thin layer of smoke due to forest fires unprecedented forest fires out east in the state. And so because of this, there was a little bit of a mad scramble to figure out how to supply the world with electricity without burning fossil fuels, without burning coal, oil, and gas. And at this point, nothing except for hydroelectric or nuclear was commercially viable. So looking at these types of green energy technologies, photovoltaics, or solar cells, had the highest potential by far to meet the need of the global economy. It had the most potential to generate the most electricity And it also did so without creating some of the ecological problems that hydropower or wind power can create, or concentrated solar power, which is a different type of solar technology that's not photovoltaics. And so because of this large potential, people were very excited about the prospect of PV technology. It's also largely noiseless too, which meant that you could put PV in neighborhoods and communities without too much pushback from different people. And the problem though is that solar was always traditionally way too expensive. And folks often thought that PV would never come down, photovoltaics would never come down in cost to the point where you could actually use it. But over the last decade, technologists working in particularly the solar industry, or in the silicon part of the solar industry, but also in the cadmium telluride part, have been able to drop the cost of solar a lot. And the market has responded very positively with year-over-year record installations in the United States and in particular globally, driven in large part by China, which has really done a great job of installing a lot of solar over the last decade or so. And the way it's been able to do this, at least on the panel side, is very interesting. The panel side being the part of interest to us material scientists. Because you think, well, they reduced the cost of solar, that means they reduced the cost of the panel, right? Well, that's not the whole story. You can lower the cost of the panel all you want, but really you're not, and that is important to try to make your process as cheap as possible, the process to make a silicon solar cell. But you're not paying for a solar cell. It's not like a car where you have the item and that is the thing that you're really looking for. You're really looking for the electricity and how cheap you can make the electricity. And so this more significant component of this price drop has been making more efficient panels. Think about it this way. If you can make 2 panels at the exact same cost, but get 10% more electricity from one than the other, even though the cost to make the panels is the same, the panel that generates more electricity is inherently cheaper because the electricity coming off of it is cheaper. Similarly, being able to make solar modules that last longer in the field, solar panels that last longer in the field, has also, from similar arguments, been able to lower the cost of solar quite a bit as well, because now you can get more electrons over the entire life of your panel, and therefore, because you don't have to spend the money to replace it, it becomes much cheaper to actually use the solar cells. And then the rest of this is financing and business stuff that I don't care about as a scientist. So, yes.
Oh yeah, one question real quick.
Yeah.
How do the solar cells like die? What causes them to reach the end of their life?
Yeah, that's a really interesting question, especially, and we'll talk about this in a little bit. I'm working in a particularly unreliable PV system material. So a lot of times they die due to moisture ingress, and the moisture, so water, humidity or water breaking through this protective plastic layer that we try to put over, that we do put on every solar cell to try to protect it from water. But it's usually corrosion and sort of atmospheric conditions that cause the materials themselves, whether it's the solar panel or the metal that you use to extract the electrons from the solar panel, to corrode and fail and no longer be conductive. So, yeah, great question. Thank you. Yeah, and so I guess just to wrap up why solar is interesting. So sunlight is abundant, and so we can generate a lot of electricity with solar. It's a fuel-free and emission-free electricity source, which means that, you know, it can help fight global warming. As of a few years ago, I can say quite confidently it's cheap and accessible to everyone. And there's little damage that solar PV can do to ecology and to human health as well. But that's great. And so the question then becomes, can we make solar better? As an engineer, you have a good technology, but that's never good enough for us. So we want to try to see if we can make solar a little bit better than it was, than it is currently with silicon technologies. I think I'll skip the prompt for the audience, but there's some ideas that people are having in the PV field that could make solar more attractive and more ubiquitous to a lot of different people. And one of these ideas is to try to make solar flexible. With the idea that currently solar panels are these, rigid, heavy, kind of ugly systems. But if you could make them really, truly flexible solar cells, you could find these new commercial products. You could put them into labels that power Internet of Things devices that tell you in real time if your food is going bad. You could have a solar charger that goes in your pocket. You could have sheets of solar cells like paper. You could forget the old solar backpacks that some of you might be familiar with that were ugly and very heavy. How about solar clothing that doesn't even look like a solar cell? Things like this are kind of the ideas that we're trying to use to make that would motivate trying to make solar flexible. Lightweight is also a significant component and directly related to the flexibility of the solar cell. You could talk about it in terms of commercial products like I did for flexible, but I think there's also a significant cost component of making your solar cells lightweight. I made the joke earlier that I don't care about the economic, the business side of trying to make solar cheaper, but that's not entirely true, because a lot of those business side things, like as I called them, aren't actually that businessy. They're related to the cost of hiring people to come and install solar on your roof, hiring an electrician to make sure you don't electrocute yourself, buying components to convert the electricity that comes, which is in direct current mode, from your solar panels into the alternating current mode that we use on our grid. And all these other sort of what we call balance of system costs, also permitting costs, things like this. And solar panels have gotten so cheap, really, that today, significantly higher than 50% of the cost of installing solar, especially if you're doing it on your rooftop, comes from things that aren't buying the panel. So again, particularly for rooftop solar, if you could imagine something like this, where you can buy a roll of solar panels from Home Depot or somewhere else, you have a peel and stick solar cell that you could install in your on your rooftop or on any bare surface in an afternoon, call an electrician to hook everything up so you don't electrocute yourself. That could be a way cheaper way of installing solar than if you had the rigid panels that need 3 men to lift onto your roof for each individual one, like you have today. Furthermore, making solar panels lightweight allows for new extraterrestrial applications, going back into space, going and trying to make solar airplanes, because again, any application where weight is money in terms of fuel in terms of liftoff and things like this, really lightweight solar could really be a game changer to bring solar technologies to these different applications. There's a question.
Yeah, why do you think that industries like the auto industry haven't really leaned into solar as much? Like we see electric vehicles and stuff. Why do you think that they haven't invested more in solar?
Yeah, and I think this is a interesting transportation question in general. So solar the amount of, if you do the we call it a back of the envelope calculation, which is just a very simple arithmetic thing that we do to try to estimate if you could make a solar car. By and large, unless you have perfect weather all the time, you really can't make a automobile that like a commercial automobile that has enough solar panels on it to generate enough electricity for the entire car. You have these very specialized cars that you can race in the Arizona desert where it's sunny all the time, and those are completely solarized. But for everyday driving, it doesn't make a ton of sense to install all these solar panels on a car. You're just not going to get the continuous amount of electricity you need to power up and do the things you need to do for day-to-day driving. So it makes a lot more sense to put the solar panels on your roof and the battery in your car. There's also other things you can do with that battery that are out of my field, but I find quite interesting. But yeah, so in terms of just trying to design a green economy that has zero emissions in its transportation sector, a lot of people have been thinking about it, and a lot of people have a consensus that the best way, most efficient, highest probability of success would be to have minimal solar on your automobile itself and just rely on fixed solar panels with a battery in your automobile powered by those solar panels. So yeah. Great. That's a great question. So, and then the last thing was, I anticipated perhaps some people thinking, well, solar panels are kind of ugly. What if we made them less ugly? And this is something that is actually not lost on us researchers. Incorporating solar panels into, excuse the dogs outside, turning the solar panels from necessity to accessory is a very interesting idea, not just for the commercial products I talked about earlier, but there's also this idea of trying to incorporate solar panels into architectural designs. This is a bit of an ambitious schematic here, but nonetheless, trying to make solar more integrated into buildings would be something, outside of just rooftops, but actually integrated into buildings would be something that's very interesting, particularly in urban environments. And there's also a cost argument on this end that I don't hear a lot of people making, but I think is quite compelling, where if you think about how we do solar today, we have these large solar fields in the middle of nowhere where no one can see them. And then we generate electricity there, and then we have to move the electricity from those areas to where people live. Now, to do that with high amounts of voltage, aka high amounts of electricity passing through, enough to power a city or partially power a city, you, as an engineer, were told, oh, it's about $1 million a mile to install the wires that you need to transmit that electricity. So as we get more and more electricity into the city itself, we can significantly reduce the need for these very expensive high voltage transmission lines connecting solar in rural areas or areas where there aren't a lot of people to solar in urban centers where there's a large amount of need for electricity. So, however, I have some bad news for how to make solar better. Silicon can't do it. Silicon is not actually going to be the way that we make these flexible, lightweight, and attractive looking solar panels. And I think it comes down to this fundamental problem, is that silicon does not actually absorb sunlight well. It's very interesting to me personally, working on next-gen solar, how silicon became the dominant technology. We are trying to create a system where we absorb light and convert it to electricity. And so we chose a material that doesn't absorb sunlight well. It's really, really quite interesting. But I think part of the reason that we chose to use silicon, or at least the folks in Bell Lab back in the 50s did, was because silicon is a material that the human race knows extremely well. And we're able to make perfect layers of silicon and work with it however we want. And so it's no problem for modern material scientists to make thick layers that are, layers that are thick enough to absorb all incident sunlight and create the efficient panels that we know today. However, these thick layers are inherently inflexible. If you don't believe me, take printer paper, try to bend 200 pieces of printer paper at a time, and then try to bend one piece of printer paper at a time. You'll see that even in the same material system, as you go to thicker and thicker layers, you're going to get inherently less flexibility. Now, the first answer is, well, why don't we just create thinner silicon? But if we create thinner silicon, we just have very bad efficiency as a result of this bad absorption. There are some light tricks that you can do to change the angle which light hits your solar cell and try to improve your efficiency, but these have not exactly worked in commercial and practical devices. And so we need to find alternative materials that have better absorbing properties to try to make these flexible and lightweight devices. And that's part of the motivation for why cadmium telluride and copper indium gallium selenide are a thing. However, with these two material systems, there's a significant problem. Because you can use much thinner layer, and in fact, you have to use much thinner layers for these more foreign materials, you need a backing. a substrate, because if you have the layer by itself, like you would in silicon, the layer will break very easily. However, to make these materials at the level you need to make efficient solar cells, you need to do 150C thermal treatments at least once. And in the case of cadmium telluride, you need multiple 500C thermal treatments. And backing materials that are flexible, you think of like paper or perhaps a metal or perhaps plastic, which plastic is the holy grail that everyone's trying to use. And none of those materials can withstand these very, very high temperatures without melting or reacting with the materials. And so we're going to need alternative to cadmium telluride and copper indium gallium selenide, or there are some systems that use copper indium gallium selenide with a very special plastic that can survive 160C. But essentially, we're going to need some creative alternative solutions to these technologies. And this is where perovskites come in. And before I talk about perovskites, I want to talk about the idea that incepted perovskites. This idea of solution processed solar cells or solution processed photovoltaics. The idea behind this sort of alternative way of making solar cells was, well, we have this high temperature problem. Let's, instead of worrying about trying to make solar cells the old ways, let's try to make a solar material that we can dissolve in an ink. And that way we don't have to worry about how hot a temperature we need to actually make the solar material, because we can deposit it on our substrate at any given temperature, our backing at any given temperature. And the ultimate dream would be, well, if we have an ink of a solar material, we could print it as quickly and easily as they print the daily newspaper, which for those too young to remember is a thing that we used to have every morning, where you could print large quantities of paper very cheaply and with very high throughput. And to try to take solar from where it is now to something that can be printed as easily and quickly as a newspaper would dramatically improve cost. And not that that much is needed anymore, but also make these really highly flexible thin film devices. And this was first thought of and incepted by this Swiss chemist, Michael Grätzel, in 1991. And his idea was very interesting because it kind of mirrors how humans have used colors through history and trying to use sunlight in various interesting ways. His idea was to try to take dyes, like the dyes that are in your shirt or in your dish towels or just, you know, in your world in general, and try to use these very good absorbing materials to make solar cells. The problem, though, is with dyes, when you have these dyes absorb light very well, but they don't conduct. And so electrons that get excited in a dye are normally just stuck in that dye until they lose their extra energy from the sun. But his idea was to take these dyes and put them on a scaffolding that has electronic conduction, titanium dioxide, or TiO2 in this instance. And actually, he was able to create a very efficient solar cell this way, at least very efficient for a first try in a lab. Unfortunately, because of various limitations with the solar cell itself, they only got to about 12%, we'll say PCE, that is a specific efficiency related to, so it's power conversion. So it's the percentage of energy of the incident sunlight that is converted to electrical energy. It was only able to get about 12% efficient at its most efficient, which is not good enough for commercialization. For reference, a silicon-based panel in the field today has about 20 to 25% efficiency, and the thermodynamic limit above which no solar cell by itself will ever achieve is 34%. And so, 12% isn't too bad because 34% is your maximum, but it's still not good enough to compete with silicon. But this was more important than just the dye itself, because it gave people the idea that gave chemists, material scientists, a whole new class of researchers, the idea that they could contribute and make new types of solar cells and solar panels. And so the next idea was to try to, tackle two birds with one stone. Not only will we replace these non-conductive dyes, but we want to try to solve another problem, which is that there is a very narrow energy window that these dyes absorb. Solar energy, as you know, comes in all different colors, which in scientific terms means they have different energies of light coming in, a wide spectrum of light energies. Dyes absorb very well in a very narrow light energy window. Semiconductors, like silicon, have a much broader absorbance window, which is why semiconductors are exclusively the highest efficiency solar cells that we have to date. So the idea of researchers was, well, let's try to make semiconductors into dyes. And you can't do that directly with an asterisk, I'll talk about later. And so their idea was to take normal semiconducting materials, make them into nanoscopic bits, nanoparticles or quantum dots that were super, super small. And if you made them very, very small and you coated them with an organic layer, a layer of just a long carbon chain, what you could do is you could disperse them in paint thinner or a nail polish remover or things like this and print them or paint them onto substrates like you would a spray paint or something else. And this also never really achieved the efficiencies that were super commerciable, but it's in this environment that perovskites came about. And it's not just quantum dot solar cells. There are other types of solution process technologies that followed a different evolution, whether it's CZTS technologies, copper, zinc, tin, sulfide technologies, or organic technologies. They never really achieved the efficiencies they needed to compete with silicon. But then came perovskites. Tsutomu Miyasaka from the Towan University in Yokohama, Japan, had this idea that instead of trying to make nanoscopic bits of semiconductors, what if we use new semiconductors altogether that themselves dissolved very easily? And he came across these hybrid organic-inorganic perovskite materials. These perovskite materials, with the very first try making a solar panel in lab, they got or solar cell in lab, they were able to get 3 to 4% efficiency, which again doesn't sound very good, but for the very first try of making a material into a solar cell, this is revolutionary and very much worth investigating. Now, there were significant problems with this type of architecture that he was using, not the material itself, but the way that he made the solar cell together that made it very, very inefficient and very unstable, such as to the point where he will tell a story, Tsutomu Miyasaka will tell a story to this day about how at the very first onset of perovskite technologies, his grad students and postdocs would assemble a solar cell and have to run as fast as they could from the assembly to the testing to make sure the perovskite didn't completely dissolve and fall apart. And so there are a lot of problems and technical challenges that need to be overcome, but they were overcome very, very quickly. A normal type of material, a solar material, takes between 10 and 20 years to achieve 15% efficiency according to the NREL efficiency, verified efficiency charts. It takes about 20 to 50 years to get to 25% efficiency, and most solar cells never achieve 25% efficiency or have yet to and will potentially in the future. Perovskites, on the other hand, achieved all 3 metrics within a decade, really blowing all other technologies out of the water in terms of the amount of time it took to get to certain efficiency metrics. Now, again, there's a lot more research effort that went into perovskites over this time frame than, say, silicon, but nonetheless, this really shows how promising this technology is to researchers. And so what is a perovskite then? Well, perovskite is not exclusive to the solar type of perovskites that we're using to make the next generation of solar cells and solar panels. It technically refers to any crystal that has this cubic arrangement of atoms in space. But solar perovskites are unique because they have halogens and organic and inorganic components, making them very unique and is also the major reason they're able to be dissolved in common solvents. And the characteristic example, if you hear perovskite, is methyl ammonium lead iodide, which is the baseline perovskite that we use to describe solar PV in this space. So perovskites have this A site, a organic carbocation in the A site of the crystal structure, methyl ammonium being the most common, but formamidinium being also fairly common if alloyed a little bit with cesium, which is too small to be in the A site by itself. You need a very, very large cation to be in this space. The B site is almost exclusively lead. We'll talk about that in a second, and sometimes a bit of tin. And the X site is usually iodide with a bit of bromide alloying, though sometimes there's also chloride in that space as well. And perovskites are really great because, as Tsutomu Miyasaka discovered, the bulk material can dissolve very well, meaning you can deposit these perovskites from solution very easily, and allows you to have this sort of, the printed type of solar cells that we were dreaming about in the field. Furthermore, perovskites have this thing called defect tolerance. So normally in a normal semiconducting material like silicon or cadmium telluride, you have atomistic imperfections, either displacements or the wrong atom is in place of a silicon, or a silicon isn't where it's supposed to be, things like this. And that's just due to entropy. And that, while that's unfortunate, it can actually significantly, defects in normal semiconductors can significantly reduce the efficiency of the panels that you're making. But in perovskites, while this is still true, defects do make a significant difference. Perovskites are much more tolerant to defects, meaning that you can make these really, really imperfect layers with a lot of atomistic imperfections and still get very efficient solar cells or light emitting diodes or all the other applications that perovskites are being used for outside of solar. And then finally, color tunability. For those who are more technically inclined, I'm talking band gap tunability here, but the ability to tune the infrared color of the perovskite solar cell means that, while I can't see a difference in color with my eye, I can use the change in infrared color to make perovskites fit into a variety of different applications that wouldn't be accessible to a semiconductor like silicon, where you only have one color of material. Yet there are still problems with perovskites, and there's reasons that perovskites haven't become the dominant technology over silicon to date. And part of it is the significant problem, or significant advantage is also its most significant problem. The bulk material dissolves well, which means that it dissolves not just in the solvents that we need to make inks, but also water vapor. So moisture degrades these perovskites very, very quickly, sometimes on the timescale of hours to days. It also has significant instabilities in temperature and humidity and oxygen with light together. Really unfortunate for implementation, a significant barrier, but something that's been worked on quite a bit. Furthermore, true ink processing isn't really super compatible with the types of films that we make with these perovskites. The way that you make the most efficient perovskite solar cells is this thing called the spin coating process, but this spin coating process is also not compatible with the promise and idea of newspaper printed solar cells. And then finally, I'll talk a little bit about lead content and whether or not it actually is a significant concern for perovskite technologies going forward, because it is actually a bit of a question right now. So stability is something that has been traditionally a huge problem, but it's also something that's got a lot of progress and people working on trying to make perovskites as stable as possible. There are now multiple reports in literature of 1,200 hours operational stability, which doesn't sound very long. You want your solar cells to last years and years and years, but as a former grad student, 1,200 hours is about as long as I'd run an experiment before I wanted to publish something. So I think that that's a much longer metric than that. We even have perovskite solar cells, which is what I'm referring to here, can pass this standard IEC test. What do I mean when I say a standard IEC test? Well, if you get a silicon-based panel at Home Depot, it'll have a warranty for 20 to 50 years, with the idea that if your solar cell fails within that, before 20 years, let's say, the manufacturer of the panel will come and replace it for free. The IEC test is how the panel manufacturer knows that they're able to do this. So basically, do an 85 test at 85 degrees C and 85% relative humidity for hundreds and hundreds of hours. And if your solar panel can withstand that, you know as a manufacturer that you can offer these warranties and you'll still make money, and you won't have to replace many of your panels. So the fact that perovskite solar cells can pass these very strict warranty level testing is promising as well. And there's even warranties that claim that they have 25-year level warranty stability, although they're pre-product, these companies that claim this. And so I don't see any 25-year warranties yet. So as a skeptical scientist, I'm going to say I'll wait and see on that specific thing. As far as scale up is concerned, I have a YouTube video. Abby, is that possible? Can we use the YouTube video here? Yeah. Okay, hold on. Let me get to it. I should have had this up. This is on me.
That's okay. While you pull it up, I do have a quick question myself. Is there any sort of like wavelength that is more or less efficient for solar emission, I guess, or absorption?
Yeah, so there's a specific ultraviolet, infrared. So the energy of light, it's hard to describe in terms of color. The energy of light where your band gap should be, your color should be, is at about 1.1 to 1.3 electron volts. So there is a specific energy that's the most efficient. So, but anyway, so this is a video from a Polish company where they're printing a large area of perovskite solar cells, about a PhD's worth, I would say, of solar cells in about 30 seconds with very high quality and very high fidelity. It's a very impressive video for someone who has only been using perovskites as a spin-coated, in a spin-coated sample. And this is from 2 years ago. So I believe that this technology is probably well scaled at this point. And so I think that I think that scale up might not be the concern that it once was at the beginning of the inception of perovskites. Can everyone see my, or Abby, can you see my PowerPoint again? Yeah. Okay.
We're still in the YouTube video.
All right. Okay. All right, great. Okay, so anyway, so outside of that foray, so the final concern is lead toxicity. And if you talk to a lot of researchers in this field, I think they kind of dismiss the idea that lead toxicity will be an issue. And I think some of the more disingenuous arguments for this are that you have more lead currently in your car battery than you would have if you were to fill your entire roof and all your siding with lead-based perovskite solar cells. And this comes about, this argument comes about because, again, we have very, very thin layers. And so there's not actually that much lead in your panels that you're going to make. This is technically true, but the lead in your car battery is well contained, not on your roof, and is not going to dissolve in water. But to that last point, I think a more legitimate argument that lead is not going to be that significant a concern is from this paper from 2015 from an Israeli group that showed that even in the worst case scenario, where you have a perovskite solar cell that's fairly thick, thicker than you would normally use, and the lamination for the perovskite solar cell completely falls apart. So the plastic completely comes off, the protective plastic comes off your solar panel, and then it rains for 2 days in a row before you notice anything. The amount of lead that goes into your, that gets dissolved from the rain and goes into the ground is actually very low. The material completely falls apart, but it's the rest of the material. It's the halogens and it's the organic components that really dissolve more readily. The lead stays behind and gets fixed on the panel with a tiny bit of lead leaching into the soil, but not a super significant amount. Okay, so that was the line for a long time, but then a recent report from 2020 has shown that the small amount of lead that does leach into the soil is actually very bioavailable, which means that plants can easily take up this lead, as you can see here, from normal mint leaves and leaves that have been exposed to runoff from the same catastrophic failure event simulated in this paper. Lead can significantly impact can be taken up from groundwater into plants and potentially affect food supply. Now, there are a lot of caveats though with this paper, and I think there's some valid criticisms. One, they used a mint plant model organism, which is extremely bioavailable to all types of heavy metals. And so potentially this is just a specific thing for mint. We don't know if this is a larger item. And I think that and there are some valid criticisms as well of this paper, but I think it's not something that we need to ignore as a field. Perhaps getting on my soapbox for a little bit, there are ways to make perovskite solar cells that don't leach lead into groundwater. You can easily control if there is a catastrophic failure where water flows. We can create lead filters at the bottom of every solar cell. We could even do something that has been done in a recent report as well, where we mix a little bit of lead fixation molecules into either our encapsulant layer or into the solar cell itself. And in so doing, whenever the lead wants to dissolve into rainwater or any sort of water contaminant, it will instead get fixed in the solar cell, and truly near zero levels of lead contamination will happen in the water runoff. There are ways to make this material safe, but I think they can't be ignored, and something that is, I would hope, is a more significant area of research over the next 5 to 10 years, or 5 to 10 months even. Things are moving very quickly in this field. So before I finish off, I just wanted to advertise a little bit of the interesting work that I'm doing at UW at the University of Washington. And we're focused more on the stability question. We have this very unique setup that allows us to take a lot of data, not just on the how our material looks, which is the color of the material normally dictates how degraded it is, but also how electrically conductive our material is at the same time. And use these to predict how long perovskite solar cells can live in different environmental conditions. And we're trying to tackle this fundamental question. If perovskites have only been around for 11 years, how can you create a warranty for 20, 25-year levels of, of replacement if you only have 10 years of data and really only have about 8 years of real data? And so using machine learning, we're trying to take all this high throughput data that we're collecting on perovskites and how they degrade at short times, create a predictive model that we can then use to say, okay, based on the model, we can predict that this specific formulation and this specific perovskite material will be able to last 20, 25 years. And then go beyond materials into devices as well, which is a bit of a challenge, but it's something that we're focused on right now and really interested in doing. And so with that, some conclusions from the talk. Present solar without perovskites is cheap, efficient, and competes with fossil fuels on price. That wasn't a major focus of my talk, but I think it's important to note we're talking about the future of solar, but solar is here and has a present and has a present right now, presence. Researchers are looking to make solar lighter, more flexible, and more aesthetically pleasing in the future. Perovskites are our best bet for reaching these goals. But before this happens, there's a lot of work that needs to be done on stability and lead toxicity before perovskites can really be deployed at the scale that we're looking and hoping that they can be deployed at. So with that, I'd like to acknowledge all my former group members, my current boss, Dr. Hillhouse, Dr. Korgel at the University of Texas, and a close collaborator at the University of Texas, Dr. Milliron. And with that, I'd like to ask if there's any additional questions at the end of my talk. So.
I'm wondering about the timeline of using creating a photovoltaic, I guess it's the silicone solar cells compared to the solution ones, what is the last one called? The perovskite.
Yeah. Oh, so when you say timeline, what do you?
Is one of them quicker to make in the lab, or installation wise? Yeah.
Yeah. So as far as how much time it takes to make a panel. Well, comparing the lab scale timeline, I think is a little bit different because silicon's very industrially optimized already. But I think on the industrial level, it takes a lot less time to make a perovskite panel than it does a silicon panel, which means you can make a lot more, for the same number of man hours, you can make a lot more perovskite panels than you can make silicon panels. So yeah.
Would you say that
R&D is done, but sorry.
Would you say that funding in the solar field is going more towards the perovskites?
Yeah, there's a lot of work. So technology transfer services or technology transfer funding sources in the government, and even some private industry is now really focusing on perovskite startups. There is a lot of investment being done in this area, although there's also a lot of private investment and equity investment in silicon, because while perovskites are growing very quickly, silicon's still a growing industry. So, yeah.
All right, well, that concludes the rest of our questions for now. If people send them in after, I'll just chase you down in an email and get them answered. Did you have any final words for us?
Nope, that's it. Just thank you for listening and for your attention. Yep.
Thank you so much for joining us so early in the morning. We really appreciate it. Stay safe out there.
Yep, of course. All right.
All right, bye.